Thank you, Ursula, and let me start by thanking you for inviting me to present at TXRF Club. I think it's very important that we are staying connected through this COVID time, since we can't meet at different conferences and see each other. So I will try to talk to you about the role of TXRF in nanomedicine. And for that, I solicited the help of my master's student, Natasha Hayden, who will cover a couple of slides and talk about her actively open research project in connection with this topic. Most of the research that I will be talking about is part of Gabriela Mankovski's PhD work. Unfortunately, Gabriela was not able to join us, so I will try to present to the best of my ability her research. So here is the outline of the presentation. We will try to explain to you, focusing on gold nanoparticles, why it is important to look into application of TXRF in nanomedicine, where the need exists and what are the issues where TXRF can be very useful. We will talk about the method development for cancer cell gold nanoparticle quantification that we worked on in the last 5-6 years, as well as on tissue quantification based on the animal or human studies needs, and then blood as the organ that distributes gold nanoparticles in animal or human body. At the end, I will try to conclude with more broad view of nanoparticles in medicine and where TXRF research or use can be of huge help. So I'll let Natasha talk about how nanoparticles are used and why they are so important in nanomedicine. So Natasha.
Thank you, Dr. Milic. So a good place to really start with this presentation is, why do we care about gold nanoparticles? So essentially, when we look at gold in the bulk form, we know it's chemically inert, but when we shrink it down to this nanometer scale, it exhibits different chemical characteristics that have allowed for a high degree of customizability. And so it's gained a lot of traction in the past decade in medical research. So we can adjust, if we look on the figure on the left, we can change the shape, where we could have spheres, rods, shells, cages, and we see that something like a nanoshell might be more ideal for drug delivery, where we could put a drug inside of the shell, versus a solid sphere, which might be better as perhaps a contrast agent, where we want to have higher degree of attenuation. And so you can adjust this shape to better suit your application. We can also adjust the size, where it can range from anywhere from like 1 to several hundred nanometers. And this size is very important, especially if you're looking at targeting different areas of the body. You want to make sure that the size is not a limiting factor. So choosing a good size for your use. We can also adjust the functionalization. So as I mentioned, we can use it for drug delivery, but here we can use attached to the outside of the nanoparticle a drug or a radionuclide, or we can even attach an antibody that would be complementary to our target for improved targeting. And we can also, again, customize the surface coating, so we can affect the overall polarity or charge of the nanoparticle for improved targeting. So it has a lot of different applications, such as imaging, diagnostics, delivery, but our main focus is more on therapy. So it can be used for photothermal therapy, where it has high efficient conversion of light to heat. And it's also great for radiation therapy. So it has a high atomic number, so it can be used as a radiosensitizing agent. And we do see higher doses administered in therapy. And so that's really where we want to focus our research on. Next slide, please. Thank you. So when we deliver this dose to a patient, we know in the end, not 100% of this dose will actually reach the tumor. In fact, a study by Day et al. Found that through research from the past 10 years, I believe it was like 232 papers, on average, only about 0.7% will reach the tumor. So the other over 99% are distributed throughout the body, where we have larger particles primarily accumulating in the liver, spleen, and kidney, and smaller particles have a higher distribution throughout all areas, such as the blood, liver, lung, spleen, kidney, and the heart. And essentially what's happening is they are recognized in the body as foreign substances, and they are targeted by macrophages or immune cells for elimination. So we have this large amount picked up and carried to other areas of the body. Now, out of that amount actually reaching the tumor, not all of it will reach the cancer cells. So in the end, out of that 100% dose, we have only 0.0014% reaching the cancer cells. Now, if we look at the image on the right, essentially what's happening is once they've entered that blood vessel, after about 12 hours, they begin to exit the blood vessel. But the extracellular matrix here is very dense, and so it will prevent them from moving forward. And so they're kept there for a prolonged period of time. And outside of that blood vessel, there's an increased concentration of these macrophages. And so they have a better ability to pick them up since those nanoparticles are kept there for longer. So we again have these nanoparticles being picked up by these macrophages. So we end up with only 14 out of 1 million actually reaching those cancer cells. So we have a very poor cellular uptake here.
So thank you, Natasha. I want to point out to this very disappointing result, which pushes today the researchers in this community to understand and improve the uptake. And also it really shows that they need very accurate way of assessing the concentration of gold. So as Natasha hinted, in my research interests and lab, what we do is we try to enhance existing cancer therapies by combo therapies with the gold nanoparticles. And here is in short what is the clinical process for that. So you have a patient with a clinical diagnosis of a cancer. Patient is then, it's planned, it's a future cancer therapy that I'm talking about, will be injected with the nanoparticles. In this case, we are today focusing on gold nanoparticles. They will be with specific coating and functionalization developed, and they are developed to accumulate in a specific location of the tumor. And then in different types of existing cancer therapies are applied as a combo therapy, and in this case, it's radiation until the full recovery. So it is shown that these combo therapies are very effective in killing cancer cells. And on the left-hand side, you have when the only radiation is applied to kill the cancer cells compared to the gold nanoparticle and radiation together. And basically 23 decrease in the survival curve of cancer cells is achieved, meaning much better medical outcome. This is very active field of research. Gold nanoparticles are at the moment widely used, but they're not the only ones that people are looking at. There is also research of gold, silver, platinum, iron, etc. nanoparticles in different coating and different shapes. One open question is the dose per patient, which signals for the need of sensitive quantification. So what I'm trying to say today, we know the survival curves, we know what the end biological point or outcome is, which is the full recovery. What we really do not know how much we need to inject to achieve a specific recovery or outcome. We also have limited knowledge on retention of nanoparticles in body, and as Natasha hinted, a lot of them get distributed throughout the human body, and we don't know really how much they stay there and what is the kinetic. And there is a lot of other open questions in this field. Currently, the Society of Nanomedicine is using ICP to quantify nanoparticles. And as you know, it is a very good analytical method, but it has its advantages and disadvantages. One advantage is that it's multi-elemental analysis, which is good, which is what we need. It has rather low detection limit, and it is quite widely available in research institutes and hospitals. The disadvantage of ICP is very complex sample prep, which takes a lot of time and requires very detailed matrix match in your calibration, external calibration process. And that's a challenge for this use. It is costly to run, and it requires quite large sample of the volume of the sample, which is typically not present in the case of cancer therapy or nanomedicine. And sometimes it even requires whole tumor to be digested to get reasonable sensitivity. And that is typically not possible in the studies where we look for biodiversity, localization, etc. So really, it's not unideal from that point of view. So what we are proposing is to use TXRF, and since majority of the audience are experts in this area, I'm not gonna explain how TXRF works, but I'll just point to two things. It's based on the internal calibration, which is very useful for this use because it does not require matrix matching, and also the system itself, because it is by the condition of total reflection, eliminates matrix effects. The spectra of even a cell of cancer are very complex, so multi-elemental analysis is still available with this approach, which is key for the research in this area. Therefore, we propose TXRF as the method for quantification of gold nanoparticles or any other medically useful nanoparticles. And the reasons is TXRF offers multi-elemental analysis. It has trace level BP and BPN and BP levels of detection. It requires very, very small sample, and sample preparation is almost negligible compared to ICP. Small volume is required, and the measurement time is very low or small compared to ICP. So here are the specific aims that we tried to focus on in developing gold nanoparticle quantification for the use in nanomedicine. These are to basically develop the method and measurement parameters for measuring gold nanoparticles in cancer cells, and to compare the quantification to something that the community calls standard technique of ICP. The second one was to start applying the developed method for different research questions at the cellular level. And Natasha will present her project at the moment, but there are much more that we are working on. Then we developed or extended the developed method to measure gold nanoparticles in tissues to be able to support in vivo animal and in the next stage human studies. In that case, I will focus on basically investigating the sample heterogeneity, which is present in the tissues embedded with the gold nanoparticles. And we developed method for measuring gold nanoparticles in microtron sections, histological microtron sections, based on the clinical need for such measurement. Lastly, we're looking into quantifying gold nanoparticles in blood as the drug is administered through blood. So moving on to talk about the development of the method, early on it became obvious that cancer cells contain zinc, and zinc peaks overlap with gold peaks in the gold nanoparticles or solutions used for treatment. And it is therefore very important to carefully investigate peak analysis or deconvolution of the zinc and gold peaks. To do that, we looked into commercially available software that comes with Pejovic provided with the Bruker instrument. Then we looked into external software, Origin Pro, and obviously PyMCA, which is typically used in XRF community. Early on, we noticed that the amount of zinc present significantly affects our ability or the recovery rate of the system. And it became obvious that the normal fit and optimized fit available or built in the system are not providing under any condition analytically acceptable recovery rates. On the other hand, Origin Pro and Bayer's approach were good only if zinc and gold amounts were the same, providing us acceptable recovery rate. On the other hand, PyMCA performed superior to any, and it performed superior and giving us acceptable recovery rate in two conditions, which is when the zinc is less or equal to the amount of gold, the deconvolution of two peaks was achieved properly. We also looked into internal standards, and traditionally people in TXRFs use Intrium. We very early on noticed that none of the softwares gives us satisfactory recovery rate. And we interpret that with the fact that Yttrium is basically detected through K lines, while gold is detected through L X-ray lines. So we switched after testing a couple different internal sources and settled on using lanthanum. And as you can see, lanthanum basically either with PyMCA or Origin and to some extent with Bayer's is giving us acceptable recovery rates. So moving forward in my research team, we decided to use PyMCA as a fitting routine along the lanthanum as an internal standard. To test this further, we basically measured recovery rate with gold nanoparticles obtained from NIST, so standard gold nanoparticles of size of 10 nanometers in the ionic solution and organic matrix, where the organic matrix is where we will be doing quantification. And we did that with the cancer breast cells, which are MDA MB231 cell line. And most of the research that we will talk in this presentation about is based on the breast cancer cells of this line, where the NIST standard is added, the source is homogenized, dropped on the quartz disk, dried and quantified to achieve these recovery rates. We also had to look and optimize, or rather minimize, the measurement time because of the throughput that clinical world needs. To do that, we looked into two extremes, minimum and maximum concentrations that we expect in the samples, and we looked into 6 different measurement times, from 30 seconds to 600 seconds, and 2 concentrations, so lower and upper limit expected in the cells or tissues. We very clearly see that any time above 200 seconds gives us acceptable recovery rates for both concentrations. And moving forward, we decided to conduct all measurements at 200 seconds measurement. The next step is to compare the current or developed method by us to the current standard procedure of ICP. To do that, we did very thorough literature search to learn basically that ICP community uses different approaches to sample prep, and they don't have standardized method for gold quantification using ICP. So we resorted to find the most frequently used prep method and to compare the recovery rate or quantification of the TXRF to that method. To do that, the most commonly used method in the literature is depicted here. And we used, again, the cancer cells of breast cancer. We spiked or injected them with the NIST gold nanoparticle standard and also commercially available gold nanoparticles that can be purchased. We then added the internal standard lanthanum, and we had to digest everything in water bath because that's the procedure that is required by ICP. Then we split the samples in two groups. One was the sample was measured as is by TXRF, which would be the preferred method for measuring using TXRF. And in the bottom line, I'm showing what is happening with the ICP most common sample prep available in the literature. So they basically filter the digested cells through the filter, and then they match with the calibration standards and proceed to the ICP measurements. And we did the same, but proceeded directly to the TXRF. So here is where our first surprise result is noticed. If you look on the left-hand side, you have results for the breast cancer cells, and on the right-hand side, you have same results, but for the prostate cancer cells. Interestingly enough, we achieved quite acceptable recovery rate using TXRF and unfiltered method, which is based on the method we developed. But when we filtered TXRF and measured it, we achieved about more than 50% drop in the recovery rate. And it even dropped further when we measured the same sample with ICP. So basically, recovery rate of ICP AES was 74% lower than the acceptable recovery rate and the one that we obtained with TXRF. And we obtained same results in two different cancer cell lines. So in the next step, what we did, we repeated the results, but calculated number of gold nanoparticles per cell, and confirmed the significant drop in the ability to detect gold nanoparticle cells if filtration is present, and further on based on the ICP measurements. So basically, same trend was observed in cancer, breast, and prostate cells in respect of the recovery based on the NIST standard, clearly showing that ICP method widely used in the community has a problem and needs their attention. But our aim was to basically show or test the ability of TXRF to reliably quantify gold nanoparticles in organic matrices, and in this case, it was in breast and prostate cancer cells. So this basically led us to conclude that we developed proper TXRF-based method for gold nanoparticle quantification in cancer cells, and it opened a whole area of research to us. And Natasha will talk to you about quantifying of gold nanoparticles in cell lines with a specific clinical question that we are focusing on at the moment. So, Natasha.
So my research looks at quantifying cytotoxicity and cellular uptake of naked gold nanoparticles. Essentially, what we're trying to do is to examine the trend of toxicity with varying shape and size of nanoparticles, so varying those key parameters of that nanoparticle. Or in other words, we want to look at, would 10 micrograms of 10 nanometer spheres result in the same toxicity as 10 micrograms of 50 nanometer rods? So does it fundamentally depend on the absolute amount of gold taken up, or does it also have a dependence on that actual shape or size? So with our initial experiments, we looked at different incubation times from 6 to 72 hours using 10 nanometer spheres, essentially trying to see where our toxicity started to take place. And in the end, we decided to continue our following experiments with a incubation time of 72 hours, as a longer incubation time corresponds to greater signs of toxicity. And we are trying to examine those trends in toxicity. So the following experiments will examine a concentration ranging from 0 to 100 micromolars with a 72-hour incubation time. And we want to look at both 10 and 50 nanometer spheres and 10 and 50 nanometer rods. Next slide, please. So here, essentially, we have a summary of the procedure. So again, we begin by choosing the shape, size of our nanoparticle, and we incubate the breast cancer cell, which again, as mentioned by Dr. Milic, we're using MDA MB231s with naked gold nanoparticles. So we don't have any coating on them. We are trying to examine the toxicity of the nanoparticle itself. So we look at naked gold nanoparticles. These cells are contained in an RPMI solution, which is a cell growth medium, with 10% fetal bovine serum, which is a cell growth supplement. So essentially you add or administer the nanoparticles to these cells, allow them to incubate for your set incubation time. And then once that's done, you can prepare them for the cell assay. So to do this, we remove the supernatant. In this case, this would contain any gold nanoparticles that were not taken up by the cells. So essentially just removing that waste. And we then follow that by trypsinizing the cells. So these are adherent cells. So they adhere to the container in which they're incubated. And so to trypsinize them, essentially we're breaking down the protein that allows them to adhere. So we can actually pick up the cells themselves. And then we centrifuge that sample so that we have a cell pellet. We can then resuspend this in a buffering solution, and we are then ready to measure their viability using our cell assay, for which we use spectral flow cytometry, which I will explain a little bit about in a second. But once we've measured the viability, we can then continue with measuring cellular uptake, which is sort of the other half of this work. With that, we use TXRF. So we begin by adding our internal standard, which, as mentioned by Dr. Milic, we use lanthanum. We then can treat the sample with our 4:1 aqua regia for our homogeneous solution. And we can prepare our quartz reflectors or our sample carriers for their TXRF measurement. And then we can put our sample on, toss that in the oven, and then they're ready for TXRF spectroscopy. So essentially, just to go quickly through the flow cytometry, so we add dyes to identify necrosis and apoptosis. So we stain these cells with APC annexin 5 and propydium iodide. Essentially, annexin 5 will indicate apoptosis, and the presence of both annexin 5 and propydium iodide will indicate necrosis, as we can see in the image on the right. So that top right would be indication of both annexin 5 and propydium iodide, whereas the bottom left, we would have no sign of either stain. So the cells are suspended in a fluid. Sorry, previous slide still. So the cells are suspended in a fluid, and this fluid is passed through narrow channels that sort the cells individually. And we then use lasers and photodetectors to measure the scatter of light on each cell, measuring both the forward and side scatter, as well as the fluorescence from any staining. Next slide, please. Okay. So here we have essentially just results from flow cytometry for our cells that were stained with annexin 5 and propydium iodide with varying concentrations of the 50 nanometer gold spheres. And this was for an incubation of 48 hours. So we can see for increasing concentration, we actually don't see any signs of toxicity in these results. So they present as healthy cells. Next slide, please. So here we have the TXRF spectroscopy results, where here on the left, we have the concentration of 10 micromolars, and on the right, we have a concentration of 100 micromolars. So in these results, if we look at the actual gold peak, we can see that while we did not see a change in toxicity, we do see a change in the cellular uptake of gold. So it is significantly higher when we increased the administration to 100 micromolars. Next slide, please. And so once we've calculated the concentration from those net peaks of the gold, we want to put this into a more applicable measurement or quantity. So we calculate for cellular uptake the number of gold nanoparticles per cell, which is using the following equation. We also, as I mentioned, want to calculate the total amount of gold or absolute mass taken up, which essentially is just the concentration of gold in ppm multiplied by the milliliters of the sample, since ppm is equivalent to micrograms per milliliter. Next slide, please. So essentially, these are the results. On the left, we have the gold nanoparticles per cell for both 10 and 50 nanometer particles or spheres. And we can see that they follow the same trend for uptake. So the 50 nanometer does exhibit higher cellular uptake overall, which is expected and agrees with theory. But if we look on the right, we can see the cellular uptake in of absolute amount of gold. And we see that the 50 nanometer actually has a more exponential increase or a much steeper slope or larger increase in that uptake of absolute amount of gold. So this is an interesting finding. However, this is ongoing research. So currently we can't really draw many conclusions from this. But with the sensitivity of TXRF, this has allowed us to measure the absolute amount, which previously, as we've seen, has not been done.
So this is just one of the examples of multiple projects that are going on right now based on the ability of TXRF to quantify reliably gold nanoparticles. And the clinical translation requires us to basically look into, can we quantify gold nanoparticles inside tissues? And that will be the next set of slides I will talk about. So basically, as you know, TXRF is designed to work for or with homogeneous samples, but in the case of tumor tissues, we don't have such privilege. We receive tumor tissues usually in slices, and we have to look into the case of spiking then with the internal standard. In other words, can we measure reliably gold in heterogeneous TXRF samples? To do that, we had to resort to Monte Carlo modeling, and we developed in the software called Topaz basically full Monte Carlo method of simulating the Bruker's Picofox TXRF instrument. And basically, the Topaz is simulation kit based on GN4. And to achieve full heterogeneity modeling, we had to resort to using Python as well. So why we had to use Python is to create the heterogeneity samples. And to do that, we created a cube, which we broke into voxels and attributed a number to each. And these voxels allowed us to assign heterogeneous composition of these samples. So we looked into 4 cases where we designed samples where gold is covered to lanthanum, meaning lanthanum is spiked on top of the sample. We reversed that in sample 2, we looked into case where the two are not the same size, and then we created an ideal sample for TXRF when the distribution is homogeneous. The outcome of the modeling showed us that we were able to detect both lanthanum and gold, but slightly different between the three samples. But what is important is that the recovery rates were very similar. So this basically allowed us to conclude that recovery rates of of gold concentrations are all analytically acceptable, ranging between 19 and 110, and therefore that heterogeneity of the sample in this approach is not an issue for TXRF. Now, I wouldn't be an experimentalist if I would believe to the Monte Carlo modeling blindly, so we proceeded to experimental testing. So what we did, we obtained fresh bovine liver, and it was frozen to -20 and prepared into microtome cuts equivalent to ones that we would receive from pathology or histology. And then they were treated in two different ways, either with gold solution or gold nanoparticle standard. And we created 4 samples, and sample 1 and 2 were prepared with certified gold solution, while 3 and 4 with the reference material in different geometries. So as you can see in the sample 1, gold layer solution is below the liver, spiked with lanthanum. Here the liver and gold are altered, and same instead of a solution with the gold nanoparticles. The samples were also imaged with scanning electron microscope to visualize the elemental distribution. And the imaging was performed directly on the TXRF refractors to ensure that the surface chemistry and topology was not altered. And as you can see, visual inspection of both samples reveals that aluminum and gold spatial distribution is uniform throughout the surface of the sample. Additionally, regardless of the orientation of the 4 samples we prepared, we obtained recovery rate within 100 and 110, meaning that the orientation or geometry of the sample did not affect the recovery rate or the way we spike samples with the internal standard. Now, logical next step would be to go and work with the tissues, but we cannot do that because we do not know the amount of gold taken by the tissue through the animal studies. So we cannot therefore determine the recovery rates from animal studies, and we resorted back to the Topaz Monte Carlo modeling. In this case, we created 2 samples, and one was considered homogeneous, where the distribution of gold lanthanum is homogeneous in the tissue, and this is again to mimic an ideal TXRF sample. While in sample 2, we layered gold into homogeneously or somehow distributed in the tissue and spiked it with the lanthanum. Interestingly enough, again, we received that the recovery rate between the 2 samples is acceptable, meaning that really in these scenarios where you have only 5 micrometers thick and 0.5 centimeters thin microtone slice, either experimentally or theoretically, the recovery rates using spiking with lanthanum are analytically acceptable. So following the tissue work, we started to look into supporting animal work where the gold nanoparticles are injected through blood in the animal. And we wanted to see if quantification of gold nanoparticles in blood can be achieved equally good. So basically, we collected blood from an animal, and whole blood was was diluted or not with water, and then lanthanum and gold solutions or standard particles from NIST were added. And the dilution with water was done at 1 to 0, 1, 1, 1.5 to 1 to 10, as well as for the reference gold nanoparticles. Since gold nanoparticles can be transported with whole blood, but they can also be transported with plasma or red blood cells, depending on the coating, we repeated the same setup basically to look into quantifying gold nanoparticles in red blood cells as well as in plasma, repeating the same setup of the experiment. So the outcome is that sample pre-treatment is necessary for blood because it's such complex matrix. And as you can see here, we basically need to dissolve either solution or gold nanoparticles to achieve reliable recovery rates. And basically acceptable recovery rates in the whole blood and plasma required 1-to-1 dilution, while for red blood cells, they required a minimum of 1-to-5 dilution factor. So in summary, basically, we managed to develop reliable sample prep for gold nanoparticle quantification with TXRF. To our surprise, the comparison to validate our approach with ICP resulted in discovering that ICP measurements and method used in the literature and by community is a problem. We moved on to using in different projects quantification at the cellular level, which turns to be very reliable and useful, addressing multiple scientific questions in that area. In respect of quantifying gold nanoparticles in tissues, we basically showed that thin slices, such as the ones as a microtone slices, can be spiked with internal standard, and direct quantification can be achieved, which is very important, as I will explain in the next slide. Blood as the transfer compartment for gold nanoparticles can be also measured, but with appropriate dilution, and therefore it is shown that TXRF can quantify gold nanoparticles in the blood. So where are we now in respect of using TXRF is that we can support any research around gold nanoparticles today in nanomedicine. So basically, we can follow combo therapies or direct therapies based on the gold nanoparticles, ideally being able to quantify the dose that needs to be injected into person or animal to achieve a medical outcome. We can also look for the biodistribution and toxicity in different elements, and therefore look into the kinetics of gold nanoparticles inside the body. We can also measure in the histology microtone slices, and therefore probably look into distribution within the organ. We definitely can reliably measure gold nanoparticles in any of the blood compartments, being whole blood, plasma, on red blood cells. And we can also aid in looking into specific therapeutic outcomes based on the methods we developed. Now, although my research or my team is focusing on gold nanoparticles, their use is wide, and we can jump easily into diagnostics or any other need and use. But that's not really the end of the story. Presently in medicine, in therapy, nanoparticles are used for silver, that are used are silver, gadolinium, iron, cesium, and many others. And in imaging, there is significant use of zinc, silicon, lanthanum, and any of these with proper method development and with the proper TXRF X-ray tube can be reliably quantified similar to the gold nanoparticles. This also means that the gold nanomedicine, the nanoparticles are not only used in medicine, there is quite large body of research in veterinary medicine, and also one that I personally think it's very interesting within the tissue engineering, which further expands the use of TXRF and shows how it can be very, very beneficial for different research areas. So lastly, I would just like to thank the sponsors of my research, ANSERC and Ryerson, and Bruker, who provided the instrument we based our research on, and Topaz and my technical team.
Let's give you a hand. Thank you so much for this highly interesting talk and sharing with us what TXRF can do in this very fascinating area. And also thank you to Natasha. I was not aware that we would have two speakers, so thank you too. And the presentation of the work is open for discussion. Yes, Stefan Seeger has a question.
Yeah, nice presentation even for me as a non-medical doctor. My question goes to the layer system with which you have checked the recovery rate in different variations. So I was a little bit surprised that this works so well, despite of reversing the geometry or even going to homogenized samples. What was the thickness actually of the layers?
5 micrometers. So I think that's the key why it works. These are microton sections and tissues are cut to 5 microns.
And the metallic layers also were 5 microns.
It's not metallic, it's gold nanoparticle solution. So it is the solution that you spike or embed into it.
Yeah, but you mentioned also the lanthanum.
Lanthanum is the internal standard, which is also spiked in the form of the solution as you would in the TXRF sample. You add solution of your internal standard.
Perhaps I misunderstood that, because I was questioning myself, what is the layer of reflection of the incoming beam in these systems?
Not metal, right? Yeah, it's not the metal, it's solution of gold nanoparticles or solution of internal standards spiked on top of the 5 micron thick tissue.
So you may then assume that always the carrier is the reflective layer or the reflective surface in all the systems.
We didn't assume, if you remember, we looked for topology with the electron microscopy. We did not assume, we checked it, and we saw the homogeneous distribution. You want me to pull that up to refresh your memory, if I can quickly find that. We did check homogeneity, right? So we didn't assume it. There we go. I can pull up this slide to show you what I'm referring to. So do you see the
we see the slides, yes. Mm-hmm.
Yeah.
So you can see that we checked when we had gold liver lanthanum versus liver gold lanthanum, that the homogeneous distribution of both is still present in the sample.
Yeah, okay. But okay, I look it up later when I look at the video.
The paper on that, Stefan, paper on that is available. Now it's published in the X-ray fluorescence under Mankowski and my last name, so you can get more information from it. It's, I think, up since a month or 2 months ago, but you can read about it. And you think in the same way as I do. I was very skeptical why it works. So that's why we did the electron imaging.
Okay, thank you so much.
Welcome.
Okay, so
now I hope my mic works a little bit better.
Yes.
My question goes in the direction of the sample preparation of the tissues. It's sometimes a little bit challenging. And how thick was your sample, and what was the drying process of the sample?
So for the tissue, as I just explained to Stefan, it is 5 micrometers, micrometers histological tissue. And to get tissue cut such thing, you have to freeze it to minimum -20, and then to use microtome to cut it in these like more films, right? It's really 5 micrometers is very, very thin. And it is already frozen, and you just put it on top of your clean silicone disc. It will adhere there, and when you spike on the gold or internal standard, they get kind of fixed to it.
Did you use the freeze dryer then for this process afterwards? To put it then in a microscope, in a scanning electron microscope, you have to put it into a vacuum and maybe before you freeze drying it, yeah?
Yeah, correct, which is how the SEM was done. Yes, that's correct.
Okay, thanks a lot.
You're welcome.
Yes, thank you. Are there more questions?
Another question regarding the limit of detection. In your presentation, you told a little bit regarding limit of detection of ICP measurements, but I got not limit of detection of TXRF of the gold nanoparticles. Do you have any numbers in this?
I do not have them with me, but we did that early on in the work, and it's already published. So I do apologize, I didn't include that at this point. But it's comparable detection limit to the ICP.
Mm-hmm.
It was very interesting to us that the recovery rates are very different. Where we focused further, the detection limit was comparable.
I believe for the TXRF, the detection limit was 10 parts per billion.
You see, young brains remember better.
Okay, more questions. I have a question that has nothing to do with the TXRF, but the nanoparticles, how they end up at the right organ at the right location. So I assume that has something to do with the stabilizers, so the shell, so the organic shell that is around the nanoparticles. And can you say what kind of functional groups are responsible or present to guide the nanoparticles to the right direction?
So, Ursula, your question is loaded. It is science on its own, but basically this slide was touching upon that. So basically, the ability to synthesize them in different size and shape, and then to surface coat them with different, there is a whole set of different coats that you can apply to them, will lead them to, let me put this up into larger view. Is that better?
Yeah.
You can see here, they're so verticile that depending where in the body you want them to go, you can code them in a different way or make them do different function to achieve your medical outcome. And it is science on its own. It's very complex and extremely diverse and attractive in a way, because we can transport any nanoparticle to any part of the body with proper design of the particles.
Yeah,
it's very complex, but it's so cool way of delivering nanoparticles where you want.
Yeah,
the body, right? And ideally, you want them only in the cancer tissue. You don't want them in the surrounding or healthy tissues. Unfortunately, that's not always 100% achieved. So you have deliveries where you don't want them, but then you want them to stay there as little as possible. You want them to be flashed out, so you can achieve that through different surface coating as well. And you also want them to be non-toxic to the other organs, which is again through material science achieved. So it's a quite complex material science problem.
Yeah, yeah, indeed. But fascinating what can be done. So
a lot of research is only on that question: how to synthesize them in a different shape and size, and then how you coat them. That's science, or magic on its own.
Yeah. Well, thank you. And I see there is another question from Heiko Till, a question from the chat incoming. How do you transfer microtome samples onto your sample carriers? How do you make sure the sample is completely flat on the sample carrier?
We transfer them with the pipette, with tweezers. They are not that thin. You can envision them as a very thin films, and if you look them, they're also transparent, but they are not impossible to transfer. It's not a complex problem, and because we spike them with different solutions, they will be flattened by that and fixed to the carrier, and that's also visible if you look back in the electron microscope images. There was a little wrinkle there. I can show you that again, but so we try to transfer them as flat as possible, but sometimes, as this image shows, wrinkles do exist, but because it's again so thin, it's not something that turned out to be of concern. So let me bring up again so I can point out to what I'm speaking about. So if you look into the tissue images, you see how it's wrinkled, and it has also different thicknesses. But because it is either 5 microns or thinner, it does not affect the outcome of recovery rate.
Okay. Yes, thanks a lot is the answer from the chat room.
You're very welcome.
Are there more questions? Doesn't seem to be the case. So I have another question. So for your future research, are you planning to switch to a different element, or are you mainly focused on the gold?
In Toronto cancer centers and research centers, there is a high need for gold nanoparticle quantification, and they are moving into animal studies. So I do anticipate that will be in the future where we will focus our interest. Nevertheless, I am looking for identifying what next gold nanoparticle could be to develop or repeat all steps as we did for gold. But again, I wouldn't do that if I can't find a research group that does intensive medical research and has the need. Showing it that TXRF can measure, I think it's not so much of value if there is no basically translating it into a clinical questions and support. So in other words, I hope to go into animal studies for gold nanoparticles, but I'm open to look into any other element that my TXRF can excite, because I have rhodium-based TXRF. So obviously I can't look into silver, for example, but I can look in iron, and there is it seems that there is a research for iron nanoparticles in my town or in Toronto that we could support, but remains to be seen.
Yeah, thank you.
You're very welcome. So Ursula, there is another question that, if time permits, I can answer. If not, I can answer to the
person. Okay, sure. So
they said slide 18. Let me just see which slide. So let me bring that up for everybody. The question is, if I understand it well, that in the both, I think, although they refer to gold nanoparticles only, yeah, that's the gold nanoparticles only, that we see less of them at these two basically bars. So the question is, why is that? The reason is filtration, because with filtration, it seems the filter itself stops not only an undigested cells, but also the gold nanoparticles. So they basically, in the way the ICP prepares its samples, there is a sample loss in the method they use, which is where the problem exists. And we just showed that in the TXRF measurements. So the problem is not the ICP itself, it's the sample prep that they widely use, at least in the community that does gold nanoparticle search. And we dig into that a little bit deeper. There is no any paper where they describe in detail sample prep and ICP measurement. So each group does it in slightly different way and their way. And there was never a chemist with ICP expertise who spent time to develop this properly and standardize for them. Does that answer the question?
Follow-up comment? Wouldn't that depend
Yes.
on the particle size and also syringe filter pore size?
Yes, I expect so. Again, I never spend time nor I plan to fix ICP issue. That's not my interest. But I would suspect, yes, for sure, both would affect the how much sample is lost in this sample prep method.
Okay, I think that now answers the question. Okay, now, very last chance, last minute question.
Perhaps one comment to the filtering issue.
Yes, please.
I believe that if you look at the filter efficiency of nanoparticles, you will see that the efficiency is of the pure particles in the range below 100 nanometers or so is near to 99%. So the particles will be filtered efficiently in such a filter, and that will probably not alone explain why the difference is so small. I would rather expect that the difference between unfiltered and filtered would be much bigger than that, what you showed, because of the high efficiency of the filters. So it's surprising that it is so low, at least from my point of view.
I wouldn't, as I said, we didn't spend time on figuring out, is it the filter, which filter we used, what they use, and reporting the literature without spending more time. So I can't comment more than that.
Yeah, remains an unsolved question at that point, right?
Yeah, we published this, pointed it out to ICP community, and it's up to them to standardize their method if they wish to.
Yeah.
I would think it's very important because if you remember, only 0.7 and 0.014% reaches the tumor. And if they are undershooting their quantification by 75%, they're really getting to very wrong medical conclusions and procedures. So it's a quite serious problem. But we published, I think, in January of last year. I didn't see any paper yet addressing this issue, which to me, they're basing their conclusions on something that's not properly done or quantified.
Yeah, unfortunately, using independent methods is not that on vogue anymore, it seems, to check your results. Okay. Okay, now I don't see any more questions. Then thank you again. And before we all leave, I like to announce the next